Professor Trevor Mudge from the University of Michigan. Professor Mudge received his PhD from another great Midwestern school, University of Illinois, and has been living in the Midwest ever since. So Professor Mudge is a Bredt family professor in Michigan. He has received many different awards for his work in computer architecture, both theoretical and practical in building various chips. And he has received the Eckert-Mauchly Award for that work, which is the highest award that computer architecture guys award themselves. And he has the requisite...
all three of us. Yeah.
Well, there's one per year, so it's a little bit more. But okay. And he has the requisite ACM and IEEE fellowships, and then the British one,
Right.
IES.
No fellowship, but anyway.
Okay. So, without further ado, I will Professor Mudge.
Okay. Thanks. Well, thanks for inviting me. It's nice to be in some sunshine. So my talk today is about this phenomenon. It's not going to be so much about neural nets as about the accelerators that people have been building. And to start with, you probably noticed that it was sort of the wisdom that back in the day, it was, you could really get hardware funded. You had an idea, tough to get venture capital for that. It's definitely changed. I counted 45, I think that's a conservative number, startups in this space that are building accelerators for, but it's mostly convolutional neural nets and deep neural nets, very similar construct. And they're, 5 of them alone have raised 100 million each. And the venture capitalists have gone over the cliff with all the other lendings, and they've sort of invested over $1.5 billion. And like I said, these numbers are sort of put together fairly quickly, so they're conservative. There's much more going on, I think. What were the driving factors? And I use the past tense because I think that the peak is over, so to speak. The driving factors were, there was a pragmatism. The unreasonable success of neural nets has had a lot to do with it. Just say a few words about that later. The slowing of Moore's law has had something to do with it. We can't just use general purpose computers. As problems get bigger, we don't have the ability to wait for the next technology node to solve the problem. So we have to build accelerators. But the accelerators, many of them, as you know, as you'll see in my talk, the application space of neural nets are very common to things that can be repurposed, like GPUs, DSP processors. That means that a lot of companies have jumped on a bandwagon and said, oh, it wasn't a DSP, it's actually a neural net processor. And the algorithms are very straightforward. And the paradigms are very familiar to many of us. But I think what's made the thing work is this order of magnitude increase in data sets. So learning things has become, we've been able to build just bigger systems that encompass more cases. And you can build these machines somewhere else because you can be fabless. TSMC is a good example of foundry, but there are many others that are popular. So that's the sort of background. Why did it happen? What were the driving factors? What are they used for? Just briefly, well, lots of different things. Computer vision is probably one of the most familiar applications. And then self-driving cars, which use vision and LiDAR and so on. Various sensor fusion ideas, but they can all be incorporated into a neural net style system. And then there's mobile things, much smaller, such as keyword spotting, Hey Siri, and medical things that are just Yeah, okay, give the talk, please. I thought I turned that damn thing off. Okay. I've got to be careful. Just remember that the next time I give the talk. Anyway, and lots of medical things that you know, like augmenting your Fitbit and so on, so that actually diagnoses what's wrong with you. So there's a unified approach here. Rather than domain experts, we can use this, if you like, all-encompassing idea of neural nets where they learn and provide a high-quality answer. And again, just to reinforce that idea, it's all based on these enormous data sets that are around. There's been lots of successes that you've seen and read about, I'm sure, the Facebook deep face, that, you know, in many cases was better than human beings at recognized faces. But of course it needs a very specific view of faces. It's not super brilliant, but for that view it's as good as a human being. And another headline-grabbing application was when DeepMind produced their Go playing machine, and in a few years, you know, it started off in 2015 being the European champion. By last year, it beat the world champion. And now if you look at Alpha Zero, which is the latest incarnation, it's actually playing itself to learn an even stronger game. So if you think things like Go and chess are intelligent activities, I don't particularly. I think they're sort of marginal. But they do impress people when you build machines that do them successfully. It should be said, by the way, that AlphaGo was not just neural nets, but it was a large component. The other component, or the other factor that's contributed to this accelerator boom is the fact that we need accelerators for lots of things now because we cannot rely on Moore's law. If you look at the history of that, the power scaling ended a long time ago, so new nodes were not giving you less power easily. The cost scaling of transistors, more recently, but it's sort of gone away. Technical limits. There's probably several nodes to go, but you can see how this whole thing's sort of grinding to a halt. And there was an article in EE Times, which is where I get all my technical information these days, that said that 2 nanometers may be the limit. So that business is in an interesting inflection point, let's put it that way. In fact, I grabbed this picture out of from the Linley Group's microprocessor report. You can see how the times between nodes, in most cases, it used to be 18 months. If you look at this for Samsung, now going to be 3 years. If you look at Intel, it's even worse. Actually, this graph is more an indictment of what's happening to Intel rather than Moore's law slowing. But you can see the general trend. There's some exceptions there, but by and large, there seems to be a conventional wisdom that says if we need things to go faster, we need to build accelerators. And that's certainly true in the DNA space. And we have fabulous, we can do it in a fabulous paradigm because we've got things like TSMC where we can offload things. Well, what were the algorithms in these neural nets? Well, matrix, vector multiplying, matrix multiplying. Been around for centuries. We know how to do that. We know efficient ways to do it. There are variations, convolution neural nets, I'll say a bit about that. But there's also, and I think maybe perhaps the most significant contributor, is this idea that we've got vast increases in the amount of data that we can use to learn things. So there are data sets now that are coming from Google, Facebook, Baidu, etc. All these FANGs have all access to large data sets, and you can add to this list Microsoft, Alibaba, FSB, who apparently know more than we do about our own direction. And this stuff is available to third parties, so they can train, you could have, this may get more difficult in the future, but you can train your DNN by buying data sets from Facebook and so on, as we heard recently in the now deceased Cambridge Analytica, who were using information from Facebook to figure out people's voting behavior. And then perhaps more interesting to this audience is the whole open source story, where you've got a lot of data sets available to you to experiment and try out new ideas that you have in this DNA space. The last thing, I've listed just a few here, AlexNet, which was one of the first, sort of a breakthrough example of application in the image processing space for the DNA technology. And then various others is Microsoft and so forth. But more recently, I don't have a lot of details on this, but there's MLPerf, which is a performance net. They're trying to build something like TCP in the database space or SPEC in the more general purpose computing space that everybody can agree on. So it's a public forum. Google and Baidu have really put together the organization, shall we say, but it includes a number of universities and other companies and so forth, to build a nice big set of benchmarks that we can all argue about and disagree about, but at least it's a stake in the ground. So it's sort of a unification of some of these other things. So that's very important. If you want to start a company, you need a way of assessing what you've done and how good it might be. So what are neural nets? Just quickly, for those that don't know about it, or I suspect I'm preaching to the choir here. The first thing, I have to put the mandatory brain picture up, because neural nets have got something to do with brains, apparently. Actually, I don't think they have much to do with brains. This is a particularly small brain. It's from the collection of University of Michigan faculty, so it's don't quote me on that one. And this idea of a neuron, it's an unfortunate anthropomorphization of this whole idea of it's a machine, it's intelligence and so on and so forth. But there's really only a passing relationship towards a neuron, which is a much more complicated beast, and in fact includes a lot more than just the things that they model incorrectly. It includes things like protein activity, chemical activity, and so on. So it's much more complicated. There's many more modes of operation in a neural network, a real neural network. But what we have is a classifier, basically, as we'll see, and it's pretty effective. And it's got these human-like terminology. So if you look at the abstraction, you have something like this, which is much simpler. It's a collection. Here's your stimulus inputs. They're weighted. They're put into some summation function and then threshold, usually. Typically with something very simple like this rectified linear unit over here. It's just doing anything negative, it throws away and replaces with 0. Otherwise, it passes on the value. That's a pretty simple thing, but it's non-linear. That has some important consequences. There have been much more complicated functions that are differentiable, as the one on the left there. So you can sort of make some, it's nice to analyze these things from an analytical point of view, but it turns out that the linear units is pretty good. So then we can connect them in what I think is probably familiar to many of you, in this network over here, which just has our neurons, that's the big circles, with the weighted sums going in and threshold function. Wait, hit the wrong button there. But the basic operation shown up on the top right, it's just a matrix of weights and a column vector of inputs. And it gives you a column vector of outputs. The big thing is that cross with a circle in it is the nonlinear operation. In our case, this rectified linear unit. And what that means is when I have a network that you can see down here with the red inputs and the turquoise inner neurons and the purple output, when I look at all of that, each layer is a matrix multiply, which, as I said, we're all very familiar with, a dense matrix multiply no less, but with this rectified linearization at each node. So we have to do the multiplies all the time because it's data dependent. And that's sort of a big unfortunate thing. It makes life more complicated. It means we need more compute power. So here's a thing I just grabbed, but you can see it's just a bunch of bipartite graphs stacked on top of each other. So it's dense matrices times dense matrices and so forth. And they can have many levels. Now, we'll look at the slight variation of this. There are many variations, but this is sort of the basic idea. What's probably the most familiar variation is the convolutional neural net, which is a little different in that, for instance, we're looking at an image over here. I don't know if you can see this pointer. I don't think it's really working very well. But the feature map here shows 4 different features. And what this system has done is rather than just learn one layer, it's learned 4 different convolutional kernels, essentially. So it's exactly like the familiar image processing idea of running a kernel across the case. And in this case, it's learned, just in this diagram, it's learned 4, and then you can continue this idea through the network until we get to fully connected networks at the back. But these are all examples of dense matrix multiplication. That's really the takeaway, and lots of it. These things are big. They're ranked hundreds of thousands in some cases, the matrices. So much for that. We've got 2 steps to the thing. I've really been talking about inference, which is the recognition classification phase. But where do we get the weights from? We get them from a learning step. And that learning step is we teach so you can see down here, we use a back propagation, in this case, showing a bunch of pictures and asking it to classify them into 2 groups, elephants or flowers. And based on the outcome, we can score the outcome, and then we start with random weights in this big conglomeration of neural nets, and then we can feed back the adjustments, usually in some sort of back propagation with a gradient descent that modifies the weights until the thing converges to a neural net. So this back propagation training phase is very expensive, very time consuming, can take days, and so on. So it's quite a lot of work on how to improve that. I'd say possibly that's where the center of gravity for a lot of the research is right now. And what you see once it's all set up, which you do much more frequently, is the inference stage, where you're just trying to use the thing to recognize elephants among flowers and so forth. So the basic algorithm just vector matrix multiply. The number of weight matrices is the depth, and then we have this simple nonlinear operation. But the thing that it lets you do is this. If it were linear, we just divide up the space with planes, or hyperplanes. But now we can use this, we can have odd-shaped things, so our classification can be more refined. And this turns out to have been quite an important step. Silly as it seems, it's not. It's quite an interesting phenomenon. So it's just this familiar dot product that we've done for years in signal processing, numerical methods, etc., etc. But with this slight twist that we do the nonlinear operation. So what that means, just as an aside here, we can't pre-evaluate our deep neural net, particularly if we can't just multiply all those matrices out and get one and use that. That would be the case if it were linear classified, but we cannot do that because there's a difference between what I'm showing at the top there, what I'm showing at the top there, which is just 3 matrices, or possibly more, being multiplied together, versus a regular matrix multiplied. What might be interesting as a direction for speeding up evaluation is if you actually subtract those two things over a set of inputs. You see the top term is dependent on that column vector. The bottom term is not dependent on the column vector. I can multiply those things out. So what I could do is actually use lots of, you find some distribution of differences, and perhaps that would, we discover that there are only a few weights that I've done the experiment a little bit, and there is an opportunity for simplification there. But it's just an aside, it's still a computationally intensive thing, even if you're doing inference. In learning, it's really a problem. Sounds like a job for accelerators, which is what it is. So what's changed? Well, I'm really hammering home the same thing. The McCulloch-Pitts neuron was, I think, proposed back in about 1943. And this is a picture from a paper circa then. It's not a whole lot different than what we're looking at today. 70 years later, no less. Which in computer evolution times is like amazingly long. There were literally a handful of computers in the world when this was being proposed. Literally a handful of computers. So things have changed. And that's part of the reason why this whole thing has been reevaluated. And there's been some countless innovations along the way. So I don't want to underestimate what's happened between McCulloch and Pitts and what we have today. There's been a lot of innovative work, but it's somewhat of a progression, sort of a regular progression, and if you couple that with large data sets to teach these things, and the ability to build very complicated but inexpensive ASICs to accelerate the neural net evaluation of memory, you can see that you can sort of get an idea, perhaps, I hope I'm convincing you, that we're at the point where this all makes sense and it's working. You can see the size, even in these early neural nets, in the modern era, let's say, you can see that they're quite memory intensive, just holding weights and things like that. I think what I should have said back when I showed you the picture of the nonlinear surfaces classifying. So what are neural nets? They're classifiers. It's not like they're intelligent. They don't think about things, as far as I know. They kind of told me. But apparently Siri was trying to tell me a few minutes ago. So what's the common denominator? What's the convergence? Dot products? Nothing more exciting than that computationally? No. Take away for computer architects, well, they're dense vectors. So that vector processing, which we know, and actually Professor Wiedenbaum has been working in this area for quite a while. He's one of the pioneers in the area, so we're all very familiar with that and how we can use it. Using existing, so NVIDIA have got GPUs, and lo and behold, they discovered they're great for deep neural nets. Sabre, which is a DSP company, have repurposed their offerings and said, look, they're really good, they do got products, so they're really good at neural nets, and so on. There's still opportunities, and that's why I think you've seen this explosion. Getting the power down, particularly if you want them to go in a mobile or something of that nature, and so on. And you can tailor precision, which, since we're doing so many multiply-add operations, can add up in terms of power consumption and also execution time. So who's on this bandwagon? But actually, the list would be shorter if I said who wasn't on the bandwagon. There's about 45, as I mentioned earlier. and they're in various applications. Self-driving cars seems to be today's idea of, or incentive, let's put it that way. But lots of other things. A recognition for security, recognition for, well, your iPhone 10 has got a face recognition in it. And actually the reason it's better than the competitors is because it has 3 cameras in there. So it's that you do need lots of data to make these things work. That's a good example. And our friends that invest in our startups have all gone crazy because they're sort of like sheep. I said lemons before, but I think lemons are smarter than sheep. And they always pump money into the thing the next guy's doing. And these days, it's building hardware. Who would have thought? I said these numbers are conservative. I'm just going to run through some of the offerings to convince you that this is the case. So we've got repurposing, starting from scratch. So Google's TPU is a good example of starting from scratch, but most of these companies are starting from scratch. They just won't reveal what's inside. We've got this key ingredient again, so they claim they have a solution. If you look at this list, it's interesting. Intel have purchased a couple of companies, as you're probably aware, Nirvana and Movidius, which were early entrants into specialized accelerators for this. And they may be inside Intel chips. I don't know the exact. As I said, it's difficult to get information on that, but I'm sure we'll find out as the next few years passes. There's a Wave, which is a group of people with a DSP background. TPU, which is the Tensor processing unit. That's the Google solution, which was a very popular paper at a recent computer architecture conference. In fact, I think it won the best paper award. And Microsoft have got an FPGA solution that's based on our old catapult idea. So Google and Microsoft are sort of at odds, which is the better solution. FPGAs are very power intensive, so that's an issue there. And I mentioned Seva, which is Seva, I'm not sure how to pronounce it correctly, but it's a company here in California that has built some, it's sort of been a leader in DSP chips. And of course NVIDIA, with their regular GPUs, and now they're announcing a TPU-like processor. I think that's every yes. There's GraphCore, which is a company that was very early and raised a lot of money. In fact, they raised over 100 million just by themselves. But they won't tell anybody. I'm on their website. I've registered and everything. They keep sending me these slideshows with absolutely no content. I mean, it's amazing that you can have 40 slides with nothing in them. But that's marketing, I guess. It's not easy to do. Anyway, and they even have a spin-off, which is 5AI, so that's how long they've been around. And then Apple, of course, have got this bionic processor that they're sticking in. So everybody's doing it, basically. And Deep 5 blocking Samsung's Galaxy 9, and then there's the China Cambrion, I should say, operation which goes into Huawei's current handset. So there's a terrific need to build these things in a small form factor with low power for the mobile space. That's probably going to be, just as it has been in most other things, the dominant use model. Self-driving cars not withstanding. They're just a lot more fun than cars. If you look at the landscape for these hardware offerings, they sort of split. I'm not going to go into the details, I just wanted to show you the idea. We've got small inference engines, relatively small, that are doing the simple classification, and then training, which tends to happen on much more heavyweight systems, and because it just requires a lot more computational work. If you look at the offerings in here, I grabbed this again from the Linley group, but the thing to take away is not the specific who's better than what, but they're all MAC operations, multiply accumulate. Is Movidius, see, it's a vector unit with a vector unit in a sort of DSP context. Here's Tensilica, which is now owned by Cadence, more vector processing units in SEMA. These are all doing dense matrix operations, and that's really the takeaway. Here's even a U of Michigan. This is something our group built, which is really low power, runs at about 300 milliwatts. It's meant for simple checking of, I was going to say, hey Siri, but I need to get away from my phone if I do that. On, off, so on, keyword recognition, essentially. The particular novelty about this is it has a hierarchy of hard memory. Somebody's listening. So, without going into that too much, but you can see that the need for a small form factor is there. I'll just spend a few minutes looking at one that's actually published details, and that's Google's TPU. Now, this is about 3 years, probably even 4 years old at this point. Because by the time they announced it, it was already a couple of years old. But it's a fairly straightforward combination that you'd expect. It's this matrix, it's a bunch of matrix multiplier units, or a bunch of multiplier units, I should say, that we can accumulate down here. There's 64,000 of these things. And if you look at the data flow down at the bottom here, you just queue up your vector elements, multiply them, accumulate them, and run them around this systolic. It's sort of a systolic model of computing. So each time around, we're doing either a full layer in the neural net, or we're doing a chunk of that layer. So you can see this thing can run pretty fast. It's running at a 700 megahertz clock. So you can, if you do the sums, you can get about 90 trillion MAC operations a second. So you can start to handle pretty big neural nets in this thing. So the idea, also there's lots of memory on board, which is important for all. You need the weights for the neural nets to be close to the processors. It was a bit of a scandal when this paper came out because Dave Patterson, in true Berkeley style, compared it against something that was like 5 years old. So I've extended this table, but originally you just look at the top line here. They compared it against NVIDIA's K80, which is, in some sense, they're certainly a lot lower power, but obviously that performance was quite a bit better. It's always an order of magnitude better. And the NVIDIA guy said, hey, wait a minute, let's look at something we built recently, the P80, Tesla P80. And you can see we're actually better than the TPU. Well, they also take a hell of a lot more energy to do that job, or a lot more power to do that job. So it's half a dozen of one and six of the other. I think what you're going to see, obviously, and you can see that sort of from this table, is if you build an ASIC, it's going to be much lower power to do the same work. But that's not a particularly brilliant observation. The usage scenarios, you should build a standard card out of these things and then start stuffing them into racks at a data center, Google's data centers, for instance. So you can actually now get access to these things through, what is it, TensorFlow, or whatever the framework is for developing DNNs. So you can actually try things out. It's a pretty simple machine. It's got 5 really big, complex instructions, which form the main part of a program for this. And it simplifies the operation pretty straightforwardly. I've just put a couple more numbers. It's not really a computer. There's no branch instructions or anything. It's purely an attached processor. And it executes out of a standard pipeline. So it's more like a sort of big FPU unit, or like Neon or SSE, let's say, in an Intel core. So what they did to keep the power down, if you notice the power's pretty reasonable, is they used, as I mentioned earlier, one thing that you can tailor is you only need limited precision arithmetic. So you can maybe use 8-bit integers as they did here, and their multipliers are much smaller. That seems to be a phenomenon. GraphCore, which has been successful at raising money and not telling us what they're doing, did actually own up to the fact that they use 8-bits. All these accelerators, and particularly once you start tailoring them, raise a big question, which is how do you program them? Not only do you have to program them as an attached processor, but you have to worry about precision and how you're going to manage that. So this is not, it's not a simple job. So you may have jobs yet, and we won't automate this for a while. Actually, it's interesting to see what's happened at Google's. Their recent offering is this TPU 2.0, and they decided that they want it to be useful for training, the learning phase, which is usually done with floating point, because you need to keep precision around when you're doing gradient descent algorithms and so on, so they don't go unstable. So this thing is actually, it's quite a bit slower. It's 45 teraflops, and the other one was about 92, if you remember. Even though this isn't a more modern technology, and it's using 32-bit floating point, although they do limit precision in the accumulate phase. I couldn't get the power consumption, but the chip itself has just got two of these things with 128 by 128. So quite a little bit, significantly fewer, I should say, multiplying units, but of course they're much bigger. And that appears to be a trade-off, because they're going to use these for inference as well as learning. It's just trying to rationalize what goes into that data set. So you can see a picture of a car here at the bottom. It's got a nice, elegant thing, but this thing here is a big heat sink. The thing, presumably is consuming some power to get that number. So what are we going to do? What's an opportunity here? We've got these dense matrix multipliers in our neural net. You can see some of the figures that we had in some earlier slides above there for AlexNet and so on. Large models, they're going to get bigger. We said one of the great features of this revolution, if you like, it's one of these things where quantity has ended up giving us a qualitative difference. And that means we're going to use bigger data sets, and that means we're going to have bigger neural nets. That's going to be tough to put them in something like this. It might be acceptable for the data center style things where you've got much more access to energy and so forth. If you just break down the cost at the bottom there of different operations, you can see that the biggest cost is actually getting things out of memory, partly due to the DDR memory interface, which is really a high-power solution to memory interfaces. So you see HB, high bandwidth memory coming in, which just basically redefines that to be higher bandwidth but lower power. So what can we do if we look at this profile to cut down on energy? Well, we can put everything in the cloud. That was the subject of the paper that I wrote with some of my colleagues at Michigan. Instead of the status quo over on the left there, where you do the thing, let's say on your watch, which is probably not practical, or your Fitbit, unless it's just going to figure out whether you say stop or go. But if it's actually going to do some much more refined classification, it needs to be bigger, of course. I'm sorry, on the left you're going to do it back at the data center. In the middle you're going to do it on the mobile, which is a problem. And the other thing is you could sort of cut the thing and do part of it on the mobile and part of it on the data center. Now, the problem anything being on the data center is you don't have much bandwidth to get stuff up there. So for voice recognition like Siri, which is low bandwidth, that's feasible. But if we want to start classifying complex scenes, that's going to be much more difficult. And there's a latency problem. So you could say, oh, couldn't we compress the thing? Yes, we could, but compression is just going to add latency. So there's some interesting problems there that some of you might want to think about, because I think there's some fruitful research in that direction. So how you break the thing down is an interesting thing. So I guess to go back to that paper that we wrote, my conclusion from writing it was, I don't know. The other authors were not happy with it. The results look good, but you know, it's a standard paper, right? It's got that bar graph in it in which your thing is bigger than the other guy's thing. And the y-axis is some form of beta. And it's highly dependent on what you want to actually partition. But it's clear we're going to have to do some of that. We could reduce the size. Now, I said they're going to get bigger to get better. That's not exactly true. We can do things like cut down on precision, which TPU 1.0 did. We can get rid of some of the weights, just not have a dense matrix multiply. So we can take this thing, and we can cut down, here's like a 3-level thing. You notice this is fully connected. We can just start to remove things. But we got to do it in some sensible fashion. If we remove enough of them, then neurons go. So how could we do it? Well, how are we going to do this pruning? Weight sharing, k-mean clustering, take out some and then reteach the thing, perhaps, with a reduced structure. If some of the values of the weights are sort of close to 0, throw them away, and so forth. So we've done a little bit of experimentation in this direction. And here you can see the idea where you can share weights and so forth. The problem is that you end up storing the thing as a sparse data structure, and I've just illustrated the compressed sparse row format, which is a very common way of storing sparse matrices. And you can see that it's complicated to get something. What happens when you go to a sparse data structure now is that you spend more time and more energy getting the thing that you actually want to operate on. In a dense matrix, it's pretty obvious where it is. It's just 2 coordinates, right? So here's your sparse thing. You just have all the values strung along here. In the value array, you can see 10 minus 2 and so forth. So you don't store the zeros. But now you have to have the column indices of all these spots, and then row pointers telling us where, you know, the boundary of the yellow and the green and the orange and so forth are. So essentially a hidden pointer. So you're doing some kind of pointer chasing. So this has actually led some people to think, hey, maybe we should do process near memory. Because we're actually running around looking for things in memory, and just the multiply add bit becomes less and less of a source of inefficiency. Rather, it's now the data. So we've tried to simplify things, but in a way we've got ourselves into a mess. So here's some experiments we did with AlexNet. You can see that we reduced the size of the thing to 1/5 of its original, the number of weights, basically, the number of neurons. And that actually, the raw computation, if you look at the number of adds and multiplies that you actually do, is more than cut in half. Okay, but it takes longer. It takes 25% longer to do the thing than on the dense machine, in the dense form, I should say. And on a GPU, it's horrible, because GPUs are just not set up for chasing pointers, which is kind of what you're doing. So you've saved on memory, the blue thing, and you've paradoxically cut down the number of adds and multiplies that you do, but somehow it's taking a lot longer. And the answer is, of course, because you're going through these more complex data structures. So I think that the future is actually the investment boom in the DNN thing is tailing off, we missed that bandwagon, or maybe some of you were on it, I don't know. I've been in computing for about 30 odd, maybe more years, and I've missed every bandwagon that's been. So, you know, so don't take the rest of this with a big grain of salt. But I think the future is that it's sparse data structures. It's certainly heading that way in these simple classifiers that the DNA world. And it's certainly heading that way in the analytics world, so there's a convergence there. So what are these? What can we do about these just for the last 5 minutes? Well, one project that we have, which we call outer space, because it uses the outer products to do sparse matrices. No comment on that. There's something that we've now managed to convince DARPA to help us fund our project. But the idea is really simple. It's like a vector processor, or a GPU, I should say, with a couple of differences. Each core executes its own program, but the programs are all identical, so it's a single program, multiple data kind of thing. What that means is that things can move asynchronously, and I mean asynchronously in the big sense, not that we don't have a clock in our logic. And the other thing is those yellow crossbars, they're supposed to denote crossbars, they are actually intelligent networks, so they can do combining and so forth, coalescing when you have processes going for essentially the same things. So the little processing element, the little green thing, is really just a work queue with associated addresses that it's looking for. And then it has either a cache in it or a software-defined memory, scratch pad in other words, because a lot of these sparse data structures don't have very good locality, so caches in some parts of the calculations don't work, so you'd like to be able to turn them on and off. I mean, turn them from being a cache, which is sort of like an associative thing, versus a programmed memory that holds stuff that you need to keep around, which would have been kicked out in a conventional cache replacement scenario. And this is just reconfiguring the thing with special memories. So we ran some experiments on the University of Florida's sparse suite, and sparse gem and so on, and the Stanford Network Analyzer project, which has a lot of sparse connectivity matrices associated with it. And just to jump to the bottom line here is, well, we're agreeing, of course, because we're the biggest bar at the end. It's mandatory, as I said, for all papers in our subject area to have that. You can never actually publish papers that show that your idea was worse than current. Unlike, you know, in the sciences, the real sciences, so that's a philosophical thing I've always had a bit of a problem with. We can never show that something maybe isn't a good idea. Anyway, I'm getting off the subject. Here are the layout patterns of these various matrices. They're sparse. What it does is it does a lot better than, for instance, the Intel math kernel on these, on just multiplying matrices together from these sets. And quite a bit better than CU sparse, which is, I think, an open source for NVIDIA processors. And it does it at a fairly modest budget of about 24 watts. In fact, we built part of that earlier machine. Now, I'm not saying that's the final analysis on the whole thing. It's just the beginning. There's probably a lot of new things that we can look at. We don't have a processor near memory feature that I mentioned, which might be valuable. So there's some interesting work for those of us in computer architecture in this space too. These are just some figures from some layouts that we did. As you can see, the power and the area are quite reasonable. This is in 32 nanometer. We're building the thing in 16 nanometer technology right now. So it compares pretty well to a K40, which is admittedly fairly old, but it's using quite a lot more power to do the So that's a good point for me to stop, and I'll be happy to take any questions. Yes?
Has anyone tried making more biology-based chips? Specifically, I'm thinking you could perhaps do a binary pulse density modulation rather than using integers or floating points.
There's something not unlike that, which is the spike neural nets. The people, because as you probably know, neurons are actually, they've got spikes running through them, not weighted values. And the spikes sort of indicate the intensity by their frequency, by whether there's a group and a bunch together. It's a little more complicated than that. But so that's led to people saying, okay, if we want to go down this path, why don't we make spike neural things? So that's about all I know. I'm sure there's more going on in that space, but I can't point to it. Yeah.
Have you looked at the possibility of coarse scale sparseness and fine scale density in your?
No, but there was a time way back when I actually looked at, when I did sparse matrices more for spice simulations in those days. And so we tried to group things by places in a chip where things were heavily connected versus where they weren't, which led to the kind of thing that you're alluding to, I think. But no, I haven't looked at it at the moment. Yeah.
So I have a question. Do you have a feel how much fat are in these neural networks? So we take a problem, we say, look, TensorFlow is going to solve it for us.
Yeah.
We have no intuition of why it's working, whatever. We say it's magic.
It is magic.
So how much fat is in there? Like if you go back and go in and say, well, let's look at what these nonlinear things are doing.
Yeah. Well, that was the 2 points that, one was, what if you just treated it as a linear operation, multiplied all the things together and subtracted the result from the nonlinear operation, and you'd have some sort of correction figure. And if that was a really sparse thing, it means you only have to fix up a few things. Maybe. Don't know the answer. The other thing was just the pruning of networks. You can cut lots of stuff out and you can make much difference. But then you can hit some, this is the problem, there's no calculus in this space. You know, you can hit one thing and it really upsets the whole network. You've probably seen these URLs where people put glasses on with colors around the edges that make them look like Johnny Depp or something. It thinks that it's looking at Johnny, you know, you put this thing on it makes, because it's fooled the network into thinking you have that face. But it's a trial and error thing as far as I'm concerned. Yeah, question in the back.
Can you put a permutation network in front of the systolic array that TPU has to do what you were suggesting for your project? Maybe realign the input data or perhaps make it sparse?
I believe that's what NVIDIA is playing around with right now. And I believe that's also what Intel is doing with their little vector accelerator there. But they're adding some, I don't know this for a fact, but I think they're taking what they understand from Mobius and Nirvana that they purchased and using some of that technology in a way that you're alluding to, I think. Yeah. Okay, well, thank you for not falling asleep.